Okay, for the power in general AC circuit, for an arbitrary combination of resistors, inductors, and capacitors, the average power is generally positive, meaning that there is net energy dissipation in the circuit. However, the power dissipation is not simply the product of the voltage and current amplitudes. Instead, it depends on the phase angle between the voltage and current. So as you can see here in the diagram, the key instantaneous current represents the purple line here, while the instantaneous voltage across device the represent here is the blue curved line across the horizontal line. So, and lastly is the instantaneous power input to device is denoted by small letter P is represent here is a black curve, very curved line. So similar to an inductor, a pure capacitor does not dissipate energy on average. So if the circuit element is a pure capacitor, the voltage lags the current by 90 degrees. So the instantaneous power P is equal to VI is also sometimes positive and sometimes negative. So it indicating that energy is alternately stored and released from the capacitor's electric field. So the average power over a complete cycle is zero. So meaning that an ideal capacitor does not assume or does not consume any net energy from the AC sources. Power in a general AC circuit. So in any AC circuit with any combination of resistors, capacitors, and inductors, the voltage or denoted by the V across the entire circuit has some angle with with respect to the current or denoted by the sign small I. So the factors cause angle is called the power factor of the circuit. So here is the equation for the average power into general AC circuit where P sub AB is equal to 1 half multiplied by V, which indicates or represents as the voltage, and I is the current cos the phase angle of voltage with respect to the current is equal to V sub RMS times the IRMS cos the phase angle of voltage with respect to the current. So resonance in AC circuits. Shown here are the graphs of R, X sub L, X sub C, and Z as a functions of the log angular frequency. So as the frequency increases, X sub L increases and X sub C decreases. So hence there is always one frequency at which x sub L and x sub C are equal and x sub L minus x sub C is 0. So here at this frequency, the impedance Z has its smallest value is equal simply to the resistance. So impedance Z is less at the angular frequency at which x sub C minus x sub is equal to x sub L. Well, the representation of the log angular frequency is the logarithmic scale. So resonance in AC circuits. Shown is a graph of current amplitude represented by the I as a function of the angular frequency. For an LRC series circuit with V is equal to 100 volts and L is 2.0 Henry and the capacitance is equal to 0.50 mF, and three different values of resistance are. So as you can see here, the in our graph is the lower a circuit's resistance, the higher, the sharper is the resonance peak in the current near the resonance angular frequency. So as you can see here, the 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 resonance peak is getting higher as the the lower circuit's resistance is. So resonance in AC circuit. So as we vary the angular frequency represented by the sign of the source, the maximum value of I occurs at the frequency at which the impedance, which is denoted by this big letter Z, is minimum. This peaking of the current amplitude at a certain frequency is called the resonance, while the angular frequency as represented is the sign at which the resonance peak occurs is called the resonance angular frequency. Here is at angular frequency is equal to the resonance angular frequency of an LRC series circuit, which the inductive reactance X sub L and capacitive reactance X sub C are equal, so the resonance angular frequency of the LRC series circuit L is equal to V is equal to 1 over the resonance angular frequency is equal to 1 over the square root of the LC.